Today we discuss system of linear equation. Okay, obviously we call about some equivalent systems. Okay, that means some system of linear equations are equivalent. So we proceed now. We start from one definition. Okay, we start from one definition. Two system of linear equation are called two system of linear equations to system of linear equations, okay, are called equivalent, are called equivalent, okay, if they have the same solution set, if they have the same solution set, okay. Two systems of linear equations are equivalent if they have the same solution set. Understood? And now we proceed further. Then we discuss one theorem related to that topics. Okay. Let Ax equal to B be a system of M linear equations. Be a system of M linear equations. Okay. Then in n unknowns, okay, and let's see be an invertible, okay, M cross M matrix, invertible M cross M matrix. Then the system okay, CAX equal to CB is equivalent to AX equal to B. Understood? Then what happened? We're going to prove of that. Okay. This theorem says that means the system CAX equal to CB is equivalent to AX equal to B. Okay. So we now write proof of that. Here, let K be the solution set for Ax equal to B. Let K be the solution set for Ax equal to B. Okay. And K dash be the solution set, and K dash be the solution set, okay, for CAX equal to CB. Understood? Then what happened? Then if W belongs to K, then what happened? Then AW equal to B. Okay. So CAW equal to CB. So CAW equal to CB. Understood? Then what happened? Then and hence W belongs to K dash. Hence W belongs to K dash. Okay, we erase our portion and going to further discussion of that. What happened now? So we proceed, and hence W belongs to K dash. Okay. Therefore K subset of K dash. Therefore K subset of K dash. Okay. Then what happened? Conversely, if W belongs to K dash, okay, then CAW equal to CB. Okay, if W belongs to K dash, then CAW equal to CB. Hence, what happened? Hence, AW equal to, okay, C inverse of CAW. Okay, then what happened? Then this one equal to C inverse of CB. Okay, this one we put here. Then what happened? This equal to B. Understood? Then so W belongs to K. Okay, that means CAW equal to CB implies that AW equal to B. So W belongs to K. Thus what happened? Thus K dash subset of K, and hence K equal to K dash. Okay, understood? Not a problem at all. K equal to K dash. Now we erase that portion and going to further discussion of that. Okay. Now we write corollary. Okay. Now we write corollary here. Let AX equal to B be a system. AX equal to B be a system of M linear equations. System of M linear equations. Okay. In n unknowns. In n unknown. Okay. And let C be an invertible M cross N matrix, and let C be an invertible M cross N matrix. Invertible M cross M matrix. Okay. Then what happened? Then the system. Okay. System. Let AX be a system of M linear equations in n unknowns. Sorry, here some mistake is happened. Okay, that means this one is not in here. Okay, so we do some mistake. If an AX equal to B be a system of M linear equations in n unknown, and if, okay, A dash augmented B dash is obtained from A augmented B, okay, by a finite number of elementary row operation. Okay, elementary row operation. Okay, then the system A dash X equal to B dash, okay, is equivalent to the original system. Understood? Then what happened? That means This augmented matrix A dash B dash is obtained from augmented matrix AB by a finite number of elementary row operations. Then the system A dash X equal to B dash is equivalent to the original system. Okay, so we now prove that. So we erase that portion and going to further discussion of proof. Okay, so now we erase that portion. Then we discussion some proof. We write it here, proof. Okay, suppose that a dash augmented b dash, okay, is obtained from a augmented b, okay, by elementary row operation, by elementary row operation. Okay, this may be that means this may be executed by multiplying a augmented b. This may be executed, okay, by multiplying a augmented b matrix, okay, by elementary m cross by elementary m cross a matrices, okay, here e1 e2 ep, understood, and let c equal to ep minus 1 e2 e1, okay. Then what happened? Then a dash b dash equal to, okay, c of ab equal to cacb, understood. Then what happened? Since each ei is invertible, since each ei is invertible, okay, since each ai is invertible, so it's c, okay. Now a dash equal to ca, now a dash equal to ca and b dash equal to cb, okay. Then what happened? Thus the system a dash x equal to b dash, a dash x equal to b dash, okay, is equivalent to the system, is equivalent to the system ax equal to b, okay, understood, not a problem at all. That means we also discuss this one. A dash augmented b dash is obtained from A augmented B by elementary row operations. Then these two systems are equivalent. Okay, so not a problem at all. We just multiplied then this elementary matrix, and obviously we then CA equal to CB, and each EI is invertible, so each C is invertible. Then A dash equal to CA and B dash equal to CB. Thus the system A dash X B dash is equivalent to the system AX B. Okay, So this one is, that means this application of this theorem we stated and proved in earlier, that means in above theorem. Okay, so now we also discuss one important definition related to that topics. Okay, that means reduced row equivalent form or matrix we discuss now. We erase that portion and going to further discussion of that. Okay, okay, now we proceed further and obviously discuss row equivalent matrix. Okay, row equivalent form of reduced row equivalent form of matrix. Okay, reduced row equivalent form of matrix. Okay, so we're going to be definition of that. Understood? A matrix is said to be a matrix is said to be in reduced row equivalent form, in reduced row equivalent form, okay, if the following three conditions are satisfied. If the following three conditions are satisfied. Conditions are satisfied. Okay. First, we write it now. Any row containing a non-zero entry. Any row containing a non-zero entry, okay, produces any row containing a non-zero entry, okay, precedes any row in which okay, all the entries are zero. All the entries are zero. That means not non-zero row. Okay, obviously that means placed in first, and then we also discuss the zero rows. Okay, any row containing a non-zero entry precedes any row in which all the entries are zero. Understood? The next option B. Okay, the first non-zero entry in each row, first non-zero entry in each row is the only non-zero entry in its column, is the only non-zero entry in its column. Okay, first non-zero entry in each row is the only non-zero entry in its column. Understood? Then that means each row containing first non-zero entry, and this is the containing some column, and this column obviously, that means just this one is a non-zero entry. Understood? Then the first non-zero entry in each row is 1, and this element is 1. Okay, the first non-zero entry in each row is 1. In each row is 1. Okay, and it occurs in a column, and it occurs in a column. It occurs in a column to the right of the first non-zero entry, right of the first non-zero entry in the preceding row. First non-zero entry in the preceding row. First non-zero entry in the preceding row. Okay, then we also show that. Okay, that means this one is the reduced row echelon form. Now we that means discuss one matrices. Okay, obviously we know about that identity matrix, one of the that means preferable matrix, which is a reduced row echelon form of matrix. Okay, now we're going to discussion of some matrices which are not belonging to reduced row echelon form. Okay, and why we also give reason. Understood? Then we now discuss this one now. In this way we write it here 1 1 0. Okay, 0 1 0 and 1 0 1. Okay, this is a matrix and is not in reduced row echelon form because the first column, which contains the first non-zero entry in row 1, obviously contain another non-zero entry. Okay, that means in first column this one is an 1 first non-zero entry, and obviously this column contains this one. Okay, so this one is not this matrix. Okay, this matrix is not in reduced row echelon form. Okay, because the first column okay, which contains the first non-zero entry, which contains the first non-zero entry, okay, in row 1 contains another non-zero entry, non-zero entry. Understood? And now we're going further discussion of that. Here the matrix 2 0 0 and 0 1 0. Okay, is not in reduced row echelon form. equivalent from, okay, because the first non-zero entry, the first non-zero entry, okay, of the second row, because the first non-zero entry of the first row, okay, of the first row is 2, not 1, okay, not 1. So this one is not not in reduced row equivalent from a matrix, okay. So that means in this way we discuss so many problems related to that topic, okay. So we also discussing another theorem related to that, okay. Obviously we now discuss another theorem related to that. We erase that portion now and going to further discussion of that, okay. We now proceed in this way. Gaussian elimination transform any matrix into its reduced row equivalent form. Okay, we write this theorem now. Gaussian elimination, Gaussian elimination, okay, transform any matrix, transforms any matrix, okay, transform any matrix into its reduced row equivalent form, into its reduced row equivalent form. Understood? Gaussian elimination transform any matrix into its reduced row equivalent form. Okay. Now we also that means say about that, known about that some Gaussian, that means some matrices, and obviously transform it into in this way, okay, some elementary operation done, and we also find some solution related to that topic, okay. But today we not discuss this one. We now going to discussion of another, that means we now discussion of another theorem related to that and proof of that, okay. And obviously first we think about that as solving a system ax equal to b, okay. We write it now. Solving a system, okay, ax equal to b, solving a system ax equal to b of m linear equations in n unknowns, of m linear equations in n unknowns, okay. The augmented matrix, okay, we need only begin to transform, okay, the augmented matrix, matrix A augmented B into its reduced row equivalent form. reduced row echelon form. Okay, A dash augmented B dash. Okay, by means of Gaussian elimination. Gaussian elimination. Okay, by means of Gaussian elimination. Understood? Now we will not further discuss today. Today I'll stop here. If you get this type of video, please subscribe my channel. And if you want to give like, please click on like option. And if you have any question, comment, suggestions, write it in comment box. So today I stop here. Thank you.